heck now? What's the molar mass of that? EBI2? There it is. So this does require some solubility rules.
Sodium.
Yeah, okay. So that's
That's
what
something I need to work on. I don't know like the types of.
okay, yes.
61 sounds about right for molar mass. We'll see.
But she's talking about the solubility rules.
Group one's always solid. Oh, so that's the okay.
Yeah, so if it's always soluble, it's going to be found in the aqueous state, not the solid, right? Yeah, so this problem, I made it to where you have to know a lot of things. You have to know your limiting reactants. You have to know or how to find your limiting reactants, and then basic stoichiometry, writing a chemical equation and predicting the products, and solubility rules. There's a lot of concepts that get tested on just one question, as we see. So it's important that maybe you know stoichiometry, but you say, okay, well, I know stoic, I'm not going to study solubility rules, but see how knowing solubility rules can impact how you do a stoichiometry problem. In this case, predicting a precipitate.
That's why he loves putting these types of questions on exams, because they test over like multiple things.
Yeah. So I think when I did this earlier, it gave me like 69 grams. Is that right? Say 69.2 or something. Okay, perfect. We'll round that to 0.2. And that's the theoretical yield, right? 69.2 grams. And then it tells us that there is actually 22 grams of precipitate collected. So it's asking for the percent yield. So what's the equation for percent yield?
Actual divided by theoretical.
Yes, so equals percent y per percent yield. So we know 22 is our actual. The 69.2 was our theoretical. This should give us something. What did y'all get? All right. So two answers here. How did y'all feel about that? Other than the
I knew it. I just
okay. Yeah, that's actually why when I made this problem, I kept using the word precipitate rather than like what the precipitate was, so that way y'all had to figure that out yourself. Do you have any questions? Anyone?
I did the converting to.
Yeah,
but it's.
okay, yeah, so you probably got stuck here, right? Because you can't do this unless you
I
know.
didn't even do the first step of making the reaction.
Yeah, yeah, good, okay, we'll take a second to explain that. So whenever we're dealing with these types of reactions where we have one salt has a cation anion reacting with another salt cation anion, usually just a double displacement reaction, unless acid base. Which that's very clear because you'll see something like you'll see a salt like calcium hydroxide with an acid like hydrochloric acid. That's obviously an acid. That's going to be an acid base reaction, even though you have your cation and anion in some sort of way.
Also just like for
Not necessarily.
what's this?
Anything that's in the aqueous state or soluble.
Yeah, or ionic, right? So in this case, metals and non-metals are gonna make your salts, right? So sodium's metal, lead's a metal, nitrate full of, it's a polyatomic anion, so it's gonna be your anion, that means you have a cation, right? And then, so you just do our double displacement, so you don't remember that, you basically, the cation of this one pairs up with the other anion, in this case, iodide, so EBI. Make sure you carry the charges over to get PBI2. And then sodium and nitrate will come together to make sodium nitrate. Yeah. So it's just a double displacement reaction. So after you get this, you know how to find the moles, right? Using the molarity equation. That gets me this part here. And then I said, okay, well, I need to get to moles of precipitate, because that's what the question's asking for. So I'm going to use my mole to mole ratio, which we get from balanced chemical equation. And then we end up finding out that this one here is the limiting reactant, sodium iodide. So then we use just, at this point, it's back to chapter 1 and 2 and 3 stuff. The only new thing really is finding which one's the precipitate. That and knowing the products is very important too. Okay. Any questions? Yes. Yeah, definitely. You have a lot of time. When's y'all test again? Is it like a week, 2 weeks from now? Okay, so 2 weeks from now. So you got plenty of time to learn your solubility rules, but don't procrastinate. I'm gonna give you a quiz. I'm gonna make a quiz and I'm gonna give it to you on Monday, okay? During our session. I expect you to know them then, and if not, I'm not gonna punish you, but we'll be able, I'm gonna score you and I'm gonna show it to everyone. How about that? There's gotta be something there that makes you motivated to not do bad.
I don't want to do bad. I'm like,
No, you're fine, just keep practicing. You being here is a good thing, so let's go to the next one. The Dean of the College of Science told you to find the original concentration of a solution that was used to prepare element 115, which is just cadmium hydroxide. They tell you that 0.5 liters of 10 molar cadmium nitrate reacted completely with 0.5 liters of sodium hydroxide. What was the original concentration of the sodium hydroxide? That's a typo. Solution, it should say solution, not concentration. What was the original concentration of the sodium hydroxide solution? What happens when you do this stuff bright and early in the morning? So I'll let y'all work on that, think about it, and you want to do this one, Rich?
Yeah.
Just got it. Your session go.
Full house.
What else?
It moves the South Commons. Long tables.
Right. Turn it off. Use this on the next exam. what charge? Which hydroxide has a minus. Not sure. I don't know if that. I guess it could exist. You see that in a lab. But like on test, you can find something that's 100 molar. So don't get skeptical. Trust the process. Want to do some pure. Okay with.
I don't know, like, I don't know if I'm that good at chemistry. I don't tend to go through.
Sure you'll be fine in organic chemistry if you study and work as hard as you are. Yeah, I found it to be a little easier because I'm honestly kind of weak when it comes to a lot of math. I mean, I just do a lot of practice and it helps out, but organic, there's like no math in there, so it's all conceptual. I'm good at understanding things on, conceptual ideas on a very deep level. I really understood OChem. So I think in general chemistry and organic chemistry, I'm way better at organic chemistry than I am at general chemistry. Yeah.
I work the exact opposite. I like math, so I can understand math a lot better than concepts. That's why I like classes like general chemistry too. They're very math heavy. And yeah. But I had found a way to turn OChem into math practically. Just memorization and just doing a bunch of problems over and over again.
Which everyone says not to memorize in organic chemistry. But it worked out for him, so it can work out for people.
When I say memorization, I don't mean memorization. I mean like doing the problems enough times to where it becomes like second nature.
Yeah.
Like, you know exactly what's going to go on in every situation. Told you, like Uncle Sam, I want you to find the original concentration, the solution that was used to prepare this thing. All right. What's my first step? Writing my balanced equation. So CdNO3 is going to react with sodium hydroxide. What are my products going to be? Sodium nitrate. That'd be CdOH. Is cadmium hydroxide soluble or insoluble? Yeah, because OH minus normally insoluble. Cadmium isn't an exception, so solid, aqueous, and aqueous. Right. Is this equation balanced? How do I balance it? 2 to the NaOH. So let's check. 1 cadmium, we're good. 2 nitrates, good. 2 sodiums, we're good. 2 hydroxides, 2 hydroxides. All right, this is the balanced equation. All right, they tell you that 0.5 liters of 10 molar CdNO3 reacted. How many moles of cadmium nitrate do I have then? Yeah, it's just 5. So 5 moles of CdNO3. All right. I want y'all to pay close attention to this phrase. It says reacted completely. What does that mean? What does that tell you? And your first thought is the correct thought. Because if it reacted completely, right? Remember, the limiting reactant is the one that gets used up quickest. So CdNO3, I'm just going to put an LR right here. This is our limiting reactant. So what that means is that it limits the amount of product that you make. Now, what element are we concerned with here? Or sorry, what compound? Or what are we trying to find? Sodium hydroxide. So how do I get from moles of cadmium nitrate to moles of sodium hydroxide? I can use the mole ratio from the balanced chemical equation. Well, if I look up, I see that for every 1 mole of cadmium nitrate, 0.32, there are 2 moles of sodium hydroxide. And that we get 10 moles sodium hydroxide. All right, now we're done, right? That's it. That's the problem. No, what is it asking? Concentration. How do we get concentration if we have moles? Moles divided by liters. So we have 10 moles. We're going to divide that by 0.5 liters. So what do we get as our final answer? 20 molar sodium hydroxide, which if you do see this, please get away because that's high concentration of sodium hydroxide. All right. All right, any questions on that? All good? Go to next one. Precipitation reaction occurs between calcium hydroxide, titanium 3 nitrate. Percent yield of this reaction, 71%. What is the actual yield? Precipitate, 60 grams of each reactant are mixed together. Apparently you saw it on a test last semester.
Is indeed another problem where you gotta know your solubility.
Oh, how's it going?
Can't believe that bad.
First semester, I printed out like 20 and reviewed the foundation exam.
How long?
What?
That's a check too, if I need.
Don't worry, you make the mistake now, you're gonna make sure you don't do that on the exam. That only means you have to erase some of the numbers. Your
Now
fault.
you learned a valuable lesson, so always check your equations balanced.
Or it's a very common thing, especially when you're like, oh, I got the products. This is it, and then you forget to balance it.
I did the reaction. I found the. What the
The solid is the precipitate, but that doesn't tell me anything else about which one it is. All right, let's write this. What did you get down for your equation?
hydroxide.
Yes, they are both aqueous or aqueous, however you want to say it.
Yes.
If they react to form,
Reactive.
Yeah.
Aqueous.
how do you know that's aqueous or aqueous?
Eight. Calcium's are.
Well, calciums were group 1, they would have a +1 charge. You know it's not a +1 because it's +2, so they are group 2. Nitrates are always soluble, yeah. So this is definitely going to be aqueous because it's a nitrate. And
Titanium.
titanium nitrate,
Hydroxide's not.
yeah, and it's titanium 3 hydroxide, right? If we were to speak about it in a sentence. Yeah, so now this is going to be our precipitate. We know that because hydroxides are generally insoluble. So there's exceptions that make them soluble, and titanium is not one of those examples. Group 1 and ammoniums and calcium, strontium, barium. All right. So how did you balance this? Or how did anyone balance this? And our reactants and products are in the same line, in the same order. Cool. Next, what did we do? Or what did y'all do? Yeah, definitely. We need to find that limiting reactant. So 60, let's just start with 60 grams of calcium hydroxide. The molar mass of that? 74. Sounds good to me. For 1 mole of Ca. And what are we doing in this little section right here? This. Wrong thing. Thing ahead of myself. So we're using the mole to mole ratio found again in the balanced chemical equation.
Why specifically titanium hydroxide though? Why that one?
So what's the molar mass now? Because we know we're looking, oh, actually, we're finding limiting reagent. But you don't need to convert all the way to grams just yet. Because like I always say, if you were taking a test, it's just another extra second that you're wasting putting it into the calculator for each one. So what did you get when you put this into your calculator? CiOH. And let's just run through this one quickly. The molar mass of this second compound reagent. 34 grams per 1 mole. So right now we're just trying to see which one's the limiting reagent. You see that this one has a mole to mole ratio of 2 to 2, so 2 to 2, that just cancels out. So what did you get when you put this into the? All right, so clearly titanium nitrate is going to be our limiting reagent. So what we can do now is, I like on a test, I would cross out this whole area because I don't want to get mixed up, especially when our points are on the line and our GPA is. I don't want to get mixed up. So now we just convert here. What's the molar mass of that one? That's going to give us how many grams of product?
Not 590.
Oh, 98. I was like, I didn't know titanium had a molar mass of that big, but okay. So 98.89. What does this give us? I'm trusting y'all on this, okay? I did it this morning. I could recognize the answer, but all these intermediate things I will not be able to tell you. All right, so now this is our theoretical yield, right? So now it's asking for our actual yield. So we know that our percent yield is equal to actual over theoretical times 100. But if you change the 71% to a decimal, you don't need to include the 100. So I'll do that. So 0.71 move the 100 times the theoretical give us our actual. It's just some simple algebra. And what happens when you do this? 18 grams. Sounds right to me. All right. Yeah, so 18 grams is our actual yield of titanium dihydroxide. So, how do y'all feel about that one? It's a percent yield question, but it's in a different sense, right? It kind of requires you to think outside the box. Normally, you're asked to find percent yield. You're not given the percent yield most of the times, but something that's totally fair game when it comes to this day, 2 weeks from now. Let's go ahead and one more. This is the last one, so we're probably gonna finish early. And if you want, you just leave. Y'all can leave, or if you have questions, you can ask questions. Yeah, so we'll give you some time to work on this. If you have any questions, let us know. To the football game tomorrow. Nice.
There's a football game tomorrow.
Yeah. I'm not going. I wanted to, but got a little stuff to do. Hopefully we win.
Already 0-1.
Yeah, we are already 0-1. That was against Houston, so I mean, you can only do so much against a team like that.
Molar chromium nitrate and 50 milliliters 4 molar lithium hydroxide. Using advanced analytical techniques and complicated jargon, student wants to determine the concentration of the nitrate ion in solution left over after the reaction. All right, David, what's my first step for anything? Any one of these problems?
Action. Balance it.
Predict the reaction or predict the products and balance it. So chromium nitrate, BrNO3, B plus lithium hydroxide. What did y'all get for the products? Chromium, BrOH3, lithium nitrate. All right. When y'all balance this, what'd y'all get? What was it? 331. Look at my Pascal's triangle out here. All right, let's check this. 331.
131.
1-3.
Oh, because I. Yeah.
All right, so let's check this. One chromium, we're good. 3 nitrates, good. 3 lithiums, we're good. And 3 hydroxides. All right. You'll notice that we don't have any moles here, but we need moles. How can we find moles? Yeah, so we have 50 milliliters for both. So 50 divided by 1,000. I'll just do it. 50 divided by 1,000. So that's 1, 2, 3 decimal places over. So that's 0.05 liters. And then multiply this times 2 for the chromium nitrate. And that one by 4 for the by 4 for lithium hydroxide. Now, what do y'all get when we do this? At 0.2 for the bottom. 0.1 for the top. So this is moles of chromium nitrate. And this is moles of lithium hydroxide. What do we do with these moles? What do we gotta do? Need to find the limiting reactants. All right, so mole ratio to our chromium hydroxide. So for every 1 mole of chromium nitrate. We have 1 mole of chromium hydroxide. So that's cool. Then we have for every 3 moles here, we have 1 mole. All right. So that being said, what is our limiting reactant? Lithium hydroxide is indeed our limiting reactant. And how many moles of chromium hydroxide do we get? We divide it out. 0.2 divided by 3. 0.06. So this, all right, so 0.066 moles of chromium hydroxide. All right. 0.066 moles of chromium hydroxide. What does this number mean?
Accessible.
Yeah, that's exactly right. So in other words, 0.066 moles of chromium hydroxide, that's how much product we made. So in other words, since we have a 1-to-1 ratio here with chromium hydroxide and chromium nitrate, that also means that 0.066 moles of chromium nitrate reacted. Normally, if this wasn't 1-to-1, you would have to do a mole ratio to solve for it. But since it's 1-to-1, we can say that this would also equal the, so this will also equal 0.066 moles of chromium nitrate. And as what was said already, we need to go back and find the excess reactant. So if we started off with 0.1 moles of chromium nitrate and we reacted 0.066 moles, how many are left over? Yeah, 3/4, right? 0.034 moles of chromium, or yeah, chromium nitrate. This is the amount of chromium nitrate left over. So I'll put left. So this is the amount that's left. Is it asking for chromium nitrate though? No, right? It's asking for the moles of, or sorry, not the moles, the concentration of nitrate ion. So how many moles of nitrate are there relative to the chromium nitrate compound? There's 3 moles. So for every 1 mole here, there's 3 moles of NO3 minus. What is that going to be equal to when you put it into the good old calculator? Sorry, 0.099 moles of NO3 1 minus. All right. Now we're done, right? That's it. No, we got to find the concentration. If we got to find the concentration, what liter amount do we have to divide by? 5.1. Yeah, exactly. So we have to use the total volume basically, right? Because we have 50 milliliters of chromium nitrate, 50 milliliters of lithium hydroxide. So imagine you have 2 beakers and then you're pouring them together in like one big beaker. The big beaker will have a volume of 100 milliliters, and that's what we want our concentration to be. We calculated the nitrate left over. Now we're going to divide it by 0.1 liters, as that is our total volume. So our answer will be what? Clearly, man like Dylan is a Juice World fan. Because we have 0.999 molar of NO3.
Problem I have is like finding the amount of sig figs at the end. So would you use molarity as? Just do milliliters.
Technically, yes, you would use the molarity in this instance, since we do have, what's it called? Yeah, since we didn't specify it was exact. So what it would be is, instead of 0.999, if you were to use sig figs, it would be just one. No decimal point or nothing, or it wouldn't matter. You can put a decimal point, but nothing after it. But let's just say for fun that we said that let's see, the molarity was exact. What would the sig figs be then? Both molarity amounts are exact. Yeah, there'd be 3 sig figs because we only use the milliliters now. So if we said they were exact, it would be 0.999. So for that, just use what you're given in the problem and then go to whatever has the least amount of sig figs.
Five. You guys follow that, or do you just do 5 and?
You should follow it, but. Yeah, you should. It is a significant. Like one of those rules.
Also, what if it's 0? Like, 0, 5, right?
If it's
So let's say it's like 3.05.
1.6, like, if it's 0.5, not 1 sig fig, we just leave it at 0.5. There's no rounding.
Yeah, but what about that?
So if it was like 3.05 and they wanted 1 sig fig, 2 sig figs,
So if it 0 is going to be considered, so you would round down to 3. It's a weird sig fig. So when there's nothing behind a 5, look at the number in front of the 5. If that number is even, round down so that number stays. If it's odd, you round up to make it even. Whatever reason they came up with it.
so like 3.15, that would turn it into 3. Because 1 is odd.
Where did you learn that? What did you remember learning it back then? And I don't remember him ever teaching it. Stop.
He didn't really emphasize it that much. And once we got it, we're taking analytical chemistry right now. So once we got there, we saw it again.
I'll just say it. Yeah. That was the last question. So yeah, if you want this worksheet so you can look in or make your own, have an idea on making your own problems and trying them out, or working with a friend and making problems and sharing problems or whatever. Send it to y'all. If not, then
Switching problem. That's an idea for future problems. Everybody makes a problem, switch to the neighbor, solve the problem.
half of the problems are not going to be solved. Your star sessions. And that would work better for organic chemistry. No, David, Megan, I don't know your name. Can I? Are you? Yeah, I'm only asking because sometimes Dr. Armand wants to know who goes to our session. So you know, Will.
No, I showed up to his office. Silence, no. Without even looking at, like, I didn't know he called me out in front of everyone. I was like, oh.
Always who goes to your sessions? So like if we're able to talk in here. And it looks good on you because it looks like you're trying. And so later in the future, if you get to know him, a letter of recommendation for whatever it is, was that you are hard work. That just looks for you.
Even from like an us standpoint, he'll like tell us the average of like people who did like come to our sessions when he gives us the name. Odds good on us, because we'll be like, say y'all scored high, we'll be like, the average for the test was like, for people who came to our sessions was like 105. So that makes people want to come more.